Hello, this is Mr. Buffington. We're going to be talking about the binomial theorem today. And this is just a quick review when we're going into the binomial theorem. When you have a binomial raised to any power, what that means is the binomial times itself. And we use the distributive property, or in this case you could use FOIL, but we would use the distributive property to multiply each term inside of the first set of parentheses times each term inside the second set, and so join like terms for your final solution. Just a quick review. Now, when you get into higher powers, like x plus y to the power of 3, you can multiply the first two together and then multiply that times the third, or, well, we just solved x plus y times x plus y, so we can just write that in, and then use the distributive property to multiply x times each of those and y times each of those. And you get this big long thing, and every time it's going to be bigger and bigger and bigger. And we'll join together like terms. I just color-coded them to make it a little bit more clear. But essentially what we're doing every single time are the same steps. So when you're asked to solve something that's really big, like to the power of 8, there really is an easier way to do it than going through and actually multiplying all of them together. So what we're going to do today is go through what we call the binomial theorem, and that is the easier way. Let's look at this. First of all, look for some patterns. You can pause the video at any time and solve on your own before I give you the answers. That'd be a good way for you to kind of keep up and see what you've learned. But look for any patterns that there are here. The first pattern that I see is the pattern of the variables. The variables will always follow this pattern. You start with x and you go 4, 3, 2, 1, 0. And then with y it's 0, 1, 2, 3, 4. Alright? They'll always follow those patterns. We don't write in y to the power of 0 and x to the power of 0. We also don't write in the 1s. But they'll follow that pattern of decreasing for x's and increasing for y's. You'll also notice that whatever power you have here, there is one term more than that. Alright, there'll always be one more term than the power. So this is 3, there's 4 terms, 4, there's 5 terms. If there were 20, there'd be 21 terms. There's always going to be one more term. Now the coefficient, the number in front of the variable here, that's actually the trickiest part. And I'm going to try and show you a pattern to solving that will help in the future for solving any point on any binomial, and that's using combinations. So when you're using combinations, you'll pick one variable, either x or y, and we're going to find the combinations of those variables. Personally, I pick y, and when I set up the combinations, I'm going to set up my combinations in proportion to y, or related to y. My combination will look like this. I'll have the total y values and then the number of y values inside of a given term. Here's what I mean by that. X plus y to the power of 4 is the same as saying this, x plus y times x plus y times x plus y. So the total y values are 4. Alright, there are 4 y values. The number of combinations that will make it have, in this case, 0 y values is the coefficient there. The number of combinations you'll take with 4 total y values that will give you just 1 is the combination, and that will be your coefficient there. So first of all, you put that number 4 in front there, and that is the total number of y values. It's going to remain constant throughout. The next value, again, I said this earlier, it's the number of y's in that term. So in this case, there's 0 y's, there's 1, there's 2, 3, and 4. And these ones are shifting over just a little bit. But that's where your coefficient is coming from. I take my total y values. How many different combinations can I make one y value with my 4? Well, 4. How many different combinations can I make 2 y values when I have a total of 4? Well, that's 6. And you'll go on, and that combination is going to be the coefficient in front of that variable. Let's do this one together, following all of those patterns, and see if we can't come up with the solution. First off, we're going to set up our variables. Remember, x starts at 5 and descends down to 0. Y starts at 0 and goes 0, 1, 2, 3, 4, and 5. All right, so our variables are all set up. Now our coefficients are going to be the combinations. So we take the total y values, which is 5, and put that in for each combination. And then the number of y's that we have in each term will go for the second number in our combination. All right? And when we solve for those combinations, we will get each coefficient here. I color-coded them this time so that we'll be sure that they correlate here and they line up. But each combination will give us the coefficient for that term. All right? And that is the solution. All right, we don't have to multiply things out 5 times to figure it out. We can just use the binomial theorem and combinations to solve. Now, there is one advantage. There are other ways to do this, but there's an advantage of using combinations, and that is that you can solve any term in the binomial expansion without having to expand the entire thing. I'll show you what I mean by that. If I wanted to solve for the third term of this binomial expansion, I would follow some patterns. First of all, I would say 5, the combination of 5 y values that will give me 2 in my term. And then I would know my variables of x to the power of 3 and y to the power of 2. Here's where the numbers actually come from. Again, the combination, total y values, the number of y values inside of any given term. And by the way, the number of y values in any given term will be that term minus 1. All right, so in this case, the third term minus 1 is 2. That's the number of y values. That's going to go here. It's also going to be the power to which y is raised. The x values are the total terms in this expansion minus whatever term you're looking for. So it's raised to the power of 5. That means there's 6 terms. This is the third term. 6 minus 3, 3. 6 minus 2 is 4. 6 minus 1 is 5. So if you follow this, you can find any binomial expansion without having to do any term in the expansion without having to do the whole thing. Let's look at this question real quick. We're looking for the 15th term of 2a minus 1 to the power of 20. I know we're doing 2a minus 1, but really, let's make it into more of an x plus y. So we'll substitute 2a equals x and negative 1 equals y. Now we have x plus y to the power of 20. We're looking for term number 15. So that's our y and that's our x value. Our combination is going to be the total number of y values, so that'll be 20. The y's in term number 15, which is 15 minus 1, so that'll be 14. And then x to the power of the total number of terms, 21, minus our term number, 21 minus 15. And then, again, the y value will be the same, 14. All right, so what we end up with is the combination 2014 with our x to the power of 6 and y to the power of 14. Now we have to substitute back in these two values that we pulled out, so x equals 2a and y equals negative 1. Oh, I solved the combination first, but that's the same thing there. So x equals 2a, y equals negative 1. We're going to plug them in and then solve for our equation. 2a to the power of 6 is 64. a to the power of 6. Negative 1 to the power of 14 is positive 1. And when we solve, we get 2,352,640, a to the power of 6. Not bad. All right. Now, what I'd like you to do is try and practice with this. Follow the same rules that we did and find the 7th term of 3a plus 2b raised to the power of 9. You can go ahead and pause the video and solve for that term. Did you get 52,457 a to the power of 5 and b to the power of 9? I hope you didn't, because that's actually wrong. Okay, time to really pause the video. Pause the video, solve for this number, and let me know what you got. All right, and hopefully your answer was 145,152, a to the power of 3 and b to the power of 6. I hope this video has been helpful for you for doing binomial expansions, and have a wonderful day.